All right, so as I mentioned to you, most of today is just going to be spent practicing a little bit more with those separable differential equations. But I do want to start a tiny bit of section 5.6 just to set us up for what we're going to do in class on Friday. 5.6 is all about modeling with differential equations, using differential equations to try to study things in the real world. Before we get into that, a couple things I just need to remind you of. So first of all, recall, derivatives give us an instantaneous rate of change of a function. Derivatives give us the instantaneous rate of change of a function. It tells us how something is changing. Derivatives give us the instantaneous rate of change of a function. So for example, if we have some function y of t that gives us the population y at time t. Oops, this up a little bit. Oh, that's not great. Let me zoom out a little bit. If we have a function that gives us the population y at time t, then y of 3 would just tell us the population at time 3. 3 hours, 3 days, whatever. And it would tell us like the number of people we have at that time. But the derivative would tell us the rate of change of the population at time 3. This is the rate of change of the population at time t equals 3. Would give us something like people per hour. This would tell us if the population is increasing, decreasing, and we're going to look way more at things like this in Unit 10. But I do just need to bring back some of these ideas to get us into why we care about these differential equations. These differential equations will all be about ways to relate rates of change to other variables. We're going to be creating differential equations that show us ways to relate rates of change with other variables. I'm going to pause for a moment so you can get those ideas in your notes. Two more things I need to remind you of, going all the way back to Algebra 2. In Algebra 2, you talked about direct variation and inverse variation. I think you probably also talked about this in chemistry. You might have talked about this in physics. Talking about things being proportional to other things or inversely proportional. Direct variation, things vary directly if things are in proportion with each other. We would say y is proportional. Oops. Y is proportional to x. Direct variation, we would call it y is proportional to x. We have our direct variation function y equals k times x, which basically says, as long as k is a positive number, if x goes up, y goes up. If x goes down, y goes down. The two things are directly related. The two things are proportional. The other type of variation you talked about in Algebra 2 was inverse variation. And you're probably more familiar with the language. Y is inversely proportional to x. And that equation would look like this. Y equals k over x. And the idea is here, again, if k is some positive number, as x goes up, y goes up. No, I said that totally wrong. Wow. Let me try that again. As x goes up, y goes down. As y goes down, x goes up. To make your denominator bigger, this thing gets smaller. Y equals kx is direct variation. Y is proportional to x. And y equals k over x is inverse variation. Y is inversely proportional to x. So we want to take these ideas of derivatives representing rates of change, combined with these ideas of being proportional and inversely proportional, to try to do some mathematical modeling. You're going to need the sheet from your Unit 9 stuff titled Modeling with Differential Equations in Class Problems. Can you please take a moment and grab that? We're going to try to create some differential equations to model various situations. In the first one, we're told the rate of change of q with respect to t is inversely proportional to the square of t. Okay, so the rate of change of q with respect to t. This is me talking about a derivative here. The rate of change of q with respect to t. With respect to t just means t is our variable. So it's kind of like I have the function q of t in this problem. If I'm talking about the rate of change of q, that would be q prime of t. Although we're going to use the notation we used in the last section, we're going to call that derivative dq dt. Now, if this is inversely proportional to the square of t, because it's inversely proportional, I'm going to do my constant, and then I'm going to put the variable in the denominator. Proportional to the square of t, it's going to be over t squared. And here's the differential equation that corresponds with that language. The rate of change of q with respect to t. That's like saying, let's find the derivative of q, and my variable is t, is inversely proportional to the square of t, equals k over, because it's inversely proportional, to t squared. The next one, the rate of change of p with respect to t. Can you tell me what that's going to look like in terms of like derivative symbols? Don't give me a prime, give me a d something else. Rate of change of p with respect to t looks like what? I think that's going to be dp dt equals, is proportional to the square of t minus 5. You got two options here. Is this going to equal k times 10 minus t or k over 10 minus t? Because it's proportional, that means direct variation, so I'm going to say 10 minus t. And there's that differential equation. Okay, so the equations we're going to look at aren't so much like 1 or 2, where I just give you things in terms of variables. They're going to be more like 3 through 6, where I give you some real-world ideas here. Number 3, barometric pressure P is changing with respect to altitude A at a rate proportional to the altitude. Barometric pressure P is changing with respect to altitude A. So first of all, this is talking about like the function P of A. You input an altitude, you get a pressure. And it's saying pressure is changing with respect to the altitude. That's going to be dP dA. It's changing at a rate proportional to the altitude. Well, that's going to look like K times A. That's my differential equation that models how barometric pressure is changing. Take a look at number 4. Rate of change of the cost C of mailing a first-class letter with respect to the weight of the letter is, let's call the weight W. The cost is a function of the weight, so it's kind of like I have C of W The rate of change of the cost with respect to the weight, that's going to be dc dw. And actually, it's not proportional to anything. It's constant. So I'm going to say that this derivative just equals the constant, k. And that's all. The rate is not changing. The rate is always what that constant is. Number 15. The rate of growth of bacteria in a petri dish is proportional to the bacteria in the dish. I'm going to say my bacteria is B. The rate of growth is kind of like saying bacteria is a function of time. You plug in various times, you find the bacteria then. Well, the rate of change of the bacteria, that's going to be dB dt. And I'm telling you it's proportional to the number of bacteria in the dish. Well, my differential equation should be dB dt equals, what's that going to look like? Proportional to the number of bacteria in the dish. I think it's just going to be k, my constant, times b, amount of bacteria you have. One more. The rate of growth of a population of field mice is inversely proportional to the square root of the population. Okay, my population is p, and rate of growth, it's like saying p of t, the population at various times. The rate of growth, you're going to make a derivative that shows that, is inversely proportional to the square root of the population. See if you can write that differential equation. I think it should be dp dt equals k, inversely proportional, so over square root of the population. This is my differential equation. So hopefully you see how we can take some ideas and create a differential equation to study them. Now our focus is going to turn to, well, how can we solve those differential equations and actually learn more about the population and all of that stuff. Back in your notes, the first differential equation that we're going to take a look at tomorrow is the differential equation for the following. The rate of change of y with respect to time is proportional to y. The rate of change of y with respect to time is proportional to y. So what this is saying is the rate of change is something with respect to time. So as times are variable, are independent variable. The rate of change of something is related to how much of that thing you have. A lot of things in the real world can be modeled with this situation. For example, population growth. The rate of change of a population is directly related to how many people you have to start with. The rate of change of a population of 50 people is going to be way lower than the rate of change of a population that has 1 million people. I'm not talking percent-wise, by the way, I'm talking like actual numbers of people in the population. If you have a city with 50 people, it's going to take a lot longer for that city to gain 10 people than if you have a city with 1 million people, for how long that city will take to gain 10 more people. The rate of change is proportional to how much of the thing you have. Now, the rate of change of y with respect to time, t, is proportional to y. I bet you can write the differential equation for that situation. That's going to look like dy dt equals k times y. By the way, k, we give a special name to this. We call this our proportionality constant. I want to go and solve this differential equation. And I can solve this by separation of variables. I know we don't have any t's in this problem. That's okay. We can solve this anyhow. Let me divide by y and multiply both sides by dt. And I can write this as dy over y equals k, my constant, dt. I'm going to integrate both sides. Integral of dy over y is the natural log of the absolute value of y. Integral of a constant, dt, is that constant times t, but then plus another constant. I've got two constants here, the one that was my proportionality constant and then my constant of integration. I want to try to solve this for y. How do we get rid of the natural log? With an e raised to the. This is e raised to the natural log of the absolute value of y equals e raised to, remember, raised to the entire side. And cancel out my e and my natural log. I'm going to make the bars just go away as well. And I'm going to say y equals e to the kt plus c. Remember the simplifying we looked at yesterday, though? I can say that that's going to be e to the kt times e to the c, and e to a constant is still just a constant. So my solution is y equals c e to the kt. I'm going to pause so you can get all this in your notes. Here's the deal. What this is really saying is any situation modeled by the differential equation y prime equals ky, where the rate of change of something is directly proportional to how much of that thing you have, as long as y is some positive amount, that has a solution of that thing I just got, y equals c e to the kt. And you've seen this before. This represents either exponential growth, something in this form, as long as k is something positive, or represents exponential decay, if k is some negative value. Again, we call that k our proportionality constant. And we're going to see that that c value up front will end up being our initial value. And I think this is all I really want to go through here. Tomorrow, we're going to apply this formula to all sorts of real-world situations to predict population, compounded interest, radioactive decay, all sorts of things like that. But right now, you're going to spend the rest of this period just doing a little bit more practice with those separable differential equations for tomorrow. I just wanted to get this head start on this stuff for tomorrow, and then we can get into all the applications when I see you in class.